Dear colleagues, behalf of the participant, I very glad to announce the talk of James Christensen. Dr. Christensen is an internationally recognized expert in the standardization and application of advanced software technologies to the automation and control of manufacturing processes. He was recognized for a lot of his achievement in pioneering application of object-oriented programming in Smalltalk with the Rockwell International Engineer of the Year and Linda Bradley Innovation Awards in 1991, and he was awarded the IEC 1906 award, and his membership in the Process Automation Hall of Fame in recognition of his accomplishments in international standardization process of programming languages, well known the IEC 6.11.31.3 standard and IEC 6.14.99 standards that intended for industrial automation for PLC control. He is currently president of HoloBlock Incorporated and Ohio Corporation. The mission of the HoloBlock Incorporation is to provide software tools, consulting and training for the application of the IEC, International Electrotechnical Commission Standard 6.14.99 for the next generation of the technology in the worldwide market for industrial automation control, so-called Industry 4.0 framework. During his 23 years career at Rockwell Automation, he led the development of the IEC 6.11.31.3 standard for programming language for programmable controllers, which has become the global standard for this segment of the automation and control market. He has also led the development of the IEC 6.15.99 standard, the successor of the previous standard for the next generation of industrial automation control. He is the author of over 30 papers, book chapter, invited lecture, and keynote addresses and keynotes, and is a senior member of ICA Association. So, dear Dr. Christensen, please, would you like to start your talk?
Okay, I'll start the screen sharing now. Let's see here. And I will start the presentation, if I can. Present, there we go.
Yes, so that's okay.
Okay, so you can all see that now?
Yes.
Okay. Okay, well, many of you are more expert than I am in new development since I've been retired for several years, although I still try to keep my hand in the standards business. So you might want to think of me as the old grandfather sitting in his rocking chair telling you about the days gone by, because we really can't understand what's going to happen in the future if we don't understand what's happened in the past. So one of the things that happened in the past, back in 2013 at the Hanover Fair, was this. That fellow over there on the right-hand side seems to be thinking, what the heck is this? But this was the presentation of the final report of the Industry 4.0 Working Group at Hannover Messe in 2013. So just to try to give you an idea of what the core of that idea was, it was this. So it was really predicting that in the future, well, now it's the future, in the future, businesses will establish global networks that incorporate their machinery, warehousing systems, and production facilities. So we're really talking mostly about manufacturing businesses in the shape of cyber-physical systems. So look at the highlighted things, especially cyber-physical systems. They would comprise smart machines, storage systems, and production facilities. And look at the capabilities carefully. Autonomously exchanging information, triggering actions, and controlling each other independently. Keep those phrases kind of in mind. And here's a nice short definition from the National Science Foundation in the US, which has been running research programs in cyber-physical systems for many years. And the definition that they settled on is a very broad definition. It's engineered systems that are built from and depend upon the seamless integration of computation and physical components. So the physical components are an important part of this. And if you look in that original Industry 4.0 report in 2013, you see that cyber-physical system platforms are at the core of the technologies for Industry 4.0. Well, as I was reading through that information, I had a case of what a baseball coach, Yogi Berra, said, deja vu all over again. Because back in the decade from 1993 to 2003, there was a program called Holonic Manufacturing Systems, which I took part in. And the objective of that project was to develop discrete, continuous, and batch manufacturing systems through integrating highly flexible, listen to the words, highly flexible, agile, reusable, and modular manufacturing units, which would be autonomous, cooperative, intelligent modules capable of automatic reconfiguration in response to new system demands and/or components. So the wording you'll see is very similar to the description of what the cyber-physical systems were supposed to be or are supposed to be and do in Industry 4.0. So the basic idea in that project, let's go back and try to remember it. This is an American philosopher with a famous saying, those who do not remember the past are condemned to repeat it. So if we look back at the Holonic Manufacturing Systems project, their idea was that systems would be built up of holons. So here's a little imaginary holon working on an assembly line. And the holon is thinking, I think and I cooperate, therefore I am, with apologies to Descartes. It does two things. It's intelligent, which means it can do smart things, and it cooperates with other holons. So the control platform for that kind of entity would be at the lower level, it would have control functions and physical interfaces, so it could, of course, operate its equipment. At the higher level, you would have software agents who would be able to communicate with each other and implement cooperation with other holons. So typically at the lower level, then the control functions would be using IEC 61499 for some reasons we'll explore later, and IEC 61131-3, of course. And at the higher layer, at that time, about the only thing we really had for developing software agents and having them communicate with each other was the Java Agent Development Environment, JADE, and the Agent Communication Language, ACL, from FIPA, the Foundation for Intelligent Physical Agents. So the motivation behind the HMS consortium was actually initially taken from the Agile Manufacturing Report, which was the report of a working group that was trying to predict for the U.S. Office of Naval Research, I think, ONR. They were trying to predict what manufacturing would look like in the 20th century. Yeah. So this is, I'm in the 21st century, sorry, 21st century. And they thought that this report predicted that the characteristic of the most profitable and leading edge industries would be they'd be able to produce to order. And this was because of increasing consumer demand for high variety and reconfigurability of consumer products. And also, to customizability, so that they'd be able to produce custom products to order. And we are actually seeing a lot of that now at a macro level. But the prediction might not be quite correct. They were predicting that the lot or batch size could be from 1 to 10,000 units, and the unit cost would be independent of lot size. Well, that's a lot to ask. And it puts heavy requirements on the manufacturing systems. They would have to be information intensive, obviously, if you're going to handle orders for customized products. If you're going to process a high variety of products in one plant, the system would need to be dynamically reprogrammable, dynamically reconfigurable, and continuously changeable, both physically as well as logically. Well, those are pretty heavy requirements. Let's look back again. That was really the motivation for HMS. What was the motivation of IEC back around 1990? Well, the IEC was confronting this dialectic between the PLC world and the distributed control systems world. And both of them were looking at the same entity supposedly the same entity called function blocks. But the PLC was looking at the use of function blocks in control systems which were centralized, they were programmable, and they were configurable. The distributed control systems people were looking at distributed and configurable use of function blocks, but not programmable. So the idea was, IEC said, can we achieve a synthesis here that will give us a common reference model for function blocks in both PLCs and distributed control systems? So what it would do is if you had a common model, you'd want to add distributability to PLC programs and add programmability to function blocks that were used in the distributed control systems. So the idea was, if you could arrive at a common architecture reference model that would be distributed, configurable, and programmable, that would solve some of these problems with the IEC. The working group thought maybe we can solve some of the problems that are needed in holotic manufacturing systems if we have a dynamically reconfigurable architecture, which would be agile. In other words, you could change where the function blocks were located, which function blocks do a job in which place. That sounds a very lot like the kinds of negotiations that go on between holons. So there was a goal to do that. What ended up happening, though, was the IEC working group that was working on function blocks and distributed control systems just went along on their merry way, and they never really achieved either programmability or agility because they were very tightly bound to field bus architecture. So they depended on the functional characteristics of field bus in order to handle the distributed control. So let's look back. How was IEC 1131.3 approaching the function of programming the programmable controllers? So it was just part 3 of a larger standard for PLCs. And what was in it? It defined standard and derived data types. In other words, derived or user-defined data types. It defined four programming languages, which were essentially procedural languages, all of them. They had two textual languages, instruction list and structured text, two graphical programming languages, ladder diagram, which mostly came from the US, and function block diagram, which came mostly from Europe. Then it defined several ways of organizing the entities that you developed in these programming languages into what they called program organization units, what we would think of today probably as library elements. But the program organization units they defined were functions, function blocks, and programs. In the most recent edition, that would be the third edition, they also defined classes and interfaces. So the original 1131 standard was adopted in 1993, maintained then by Task Force 3 of Working Group 7 of IEC Subcommittee 65B. And I was the coordinator for that work until the second edition. The third edition was issued after I retired, and that effort was valiantly led by Hans-Peter Otto of Siemens. That standard is currently in the maintenance cycle for the fourth edition, which means they will probably come out with a new work item to develop the fourth edition next year. So they're currently developing a maintenance report in which they are processing and resolving 285 comments and issues. And they're all dealing with fairly small changes, but significant corrections and additions. But it's hard to try to describe any coherent idea of what that new version is going to look like. All I can say is that it will be new and improved. I just went through and tried to make sense out of it, and it's just one comment after another. So let's wait and see what happens. Okay, what is 61499? It is not a programming language standard. It's a standardized, open and event-driven distributed system architecture for automation and control in which function blocks are the fundamental units of software encapsulation, reuse, deployment, and integration. Okay, so let's look at the highlighted areas one at a time. It's a distributed system architecture. And you can contrast that with the 1131.3 software model, where the configuration only applies to a single device. The execution model is task-driven. Different resources within the device communicate via global variables, which has long been known to be a dangerous concept. And also both the I/O and the communication are also mapped to variables, which are to some extent globally accessible. Okay. The 1499 software model, in contrast, deals with distributed applications in which each application is represented by a network of function blocks which have event flow and data flow going back and forth between them. And the applications will be mapped onto networks, and the network structure is similarly simple, maybe be mapped onto systems. So the system consists of the communication network, the devices, and then the controlled processor machines. And applications, as you see in the sketch, can be spread across devices. And the way that's done is by a mapping function. So here, for instance, in this case, these three function blocks would be distributed across the devices. But of course, then you have to be able to deal explicitly with event and data flow. And this is the big difference of this standard with the 61804 standard for function blocks in distributed control systems, process control systems. There, everything has to be mapped implicitly onto the capabilities of the underlying network. Okay. The device model, as you'll see for 1499, is similar to the 1131.3. A device contains resources, and the communication and process interfaces may be shared among the resources, and the applications may be distributed across the resources. And they may actually be distributed across devices too, as we know. Okay, so how did we get to this stage in 1499? The work began in 1992. The initial focus, as we saw before, was to resolve differences in the use of function blocks between DCS systems and PLC systems. There was also this growing emphasis on open distributed architectures for agile and intelligent manufacturing systems, which came from the HMS consortium. So 1499 was adopted in 2005. It has 3 parts. Part 1 deals with the system architecture, Part 2 with the software tool requirements, and Part 4 with rules for compliance profiles, which address the issues of portability of programs and library elements, configurability of devices by configuration tools, software tools, and interoperability of the devices. And the maintenance team is the same subcommittee of IEC as the PLC, is just another working group. And the second edition came out in 2013, and it's now in a maintenance cycle, which we'll discuss in much more detail towards the end. Okay, what actually happened? Where did the emphasis on the rapid, flexible reconfigurability come from? It actually came from the Holonomic Manufacturing Systems Consortium, whose parent organization was the Intelligent Manufacturing Systems Program, which was an international program which was started by the Japanese government, and very quickly participation started from the United States and the EU. And the particular project that we've been talking about are the HMS Consortium, and the goal was, as mentioned, intelligent manufacturing through holonic modules, which were autonomous and cooperative. So that project went on for 10 years, from 1993 to 2003, and it paralleled the development of IEC 61499. Okay, and here it was working on the standard model of function blocks for encapsulation, reuse, and distribution. So the reconfiguration emphasis came initially from HMS. And the reason those two developed in close coordination was at least 2 people were in both groups. That was myself and Dr. Rainer Mittmann from Softing outside of Munich. So let's look at the event-driven nature of the architecture of 1499. Why event-driven architecture? Because it's really the simplest and most efficient way to synchronize and sequence the execution of operations in distributed applications. So the reason it's there is to support this flexibility of distributing the application. Besides which, all modern industrial automation and control systems, such as PLC, DCS, and SCADA, are built on underlying event-driven multitasking operating systems. The operating system is event-driven anyway, so why not take advantage of that? So this is just a picture of event and data flow between function blocks and a resource. For instance, the communication comes in, it gets mapped into events and data by a so-called communication service interface function block. We'll discuss those a bit later. Events and data flowing out of the communication service interface function block cause the execution of an algorithm in a downstream function block, which then sends the data to the output through an input-output service interface function block. You can also have the reverse happening. An event happening in the physical world may cause events and data to come from the service interface function block. And in this simple diagram, that event causes the data to be sent back out over the communications service interface block. So that's a quick look at the underlying event-driven nature. Now let's look at function blocks themselves. Again, this is probably familiar to many of you, so I won't spend too much time on it, although there are several slides. Okay, the fundamental units of encapsulation, reuse, and distribution, yeah, we know that. There's event flowing coming in from the left-hand side. There's data flow coming in from the left-hand side. Something happens in the function block, and you get event flow coming out, carrying data with it. And which data is carried with which event is given by the event data association. And all of the variables in the function block use IEC 6.1131.3 data type. So there's the first dependence on 1131.3, and that's why this is not a programming language standard. It relies on 1131. Okay, basic function block types. Again, you're probably pretty familiar with this. Incoming events and variables, trigger and execution. Incoming events trigger an execution control chart, which then triggers the operation of an algorithm, which works with the input variables and possibly internal variables, produces values for some of the output variables, goes back to the execution control chart, which then triggers an event output, one or more event outputs. Okay, the execution control chart itself, you're probably all familiar with this. It's similar to the Harel state chart. It has states, transitions, and actions. The algorithms themselves are written in any suitable programming language, which could be the 1131 languages, or Java, or C++, or whatever language you can get that you can make interface through this function block structure. Okay, first level of reuse is a composite function block where there's no execution control chart. It just contains a function block network, or we might call it. Oh, I don't use the word function block diagram because that's reserved for 1131. So I use function block network, and you can see when input event may trigger one set of function blocks, and the other input event may trigger a different set of function blocks. So this is sort of reuse and algorithm selection, if you want to think of it that way, where the algorithms are actually contained in the component function blocks. Okay, so we really, in the standard, have three sort of fundamental kinds of function blocks. There are the basic function blocks, the composite function blocks, and the service interface function blocks, which give access to the services that are provided by the resource. For instance, I/O, human-machine interface, communications, other interesting things such as software agents or service-oriented architecture services. And they're modeled as sequences of service transactions according to a quite mature standard for open systems interconnection. And just as an example, this is a familiar client-server structure for communication, and what might happen in a standard. So here's down below is the model of the normal data transfer. Here's a sort of a flow diagram showing you what happens. An input event at the request of the client causes the data to be transmitted, and then an event to be triggered at the indication output of the server. The server then can respond, and with data that gets sent back, and the client then gets a confirmation event with the associated data from the server. So these are just pretty normal kinds of function block operating, like normal kinds of service transactions that can obviously be modeled here. So that was just an example, really, of using the service interface function blocks. Request and response are quite common. Also, publish and subscribe are common, which I didn't do a slide of. So let's talk about how systems are deployed and integrated in 1499. The way it's done is by device management. It's done by a function called FB Manager, and here's the software toolset over here on the left. The FB Manager is actually in the software toolset, but if the device is in the same place as the toolset can configure the device directly through a local function block manager. Otherwise, it has to be distributed. So what we did in the 1499 standard was we did a separation of concerns. We separated out the communication function from the management function. If you look at other standards, again, such as the field bus standards, it's all balled up together. And you have to understand, you have to very deeply understand the communication function in order to understand the device management function. In this case, the management function is in a device manager function block. So what happens is, let's see. So if this is local, the command just passes through to configure the device that's locally attached. If it's remote, a request goes through a client block, a management client block, into a communication client block, and then gets sent over to just a regular server communication block, which then triggers a command or a request to the device manager, which performs the management function, and then confirms. It's a local confirmation if it's local, otherwise it goes back through the communication link, and it gets a response. Okay, there it is. Okay, again, I know that many of you are very familiar with this, so we'll go quickly through it. The configuration commands themselves, that is these commands down here at the request input of the device manager, are written in XML. So the question was, how could you use this device manager to create this configuration? Well, the first thing you would create is a function block. And the next thing you would create is a second function block. Then the third thing you would do is you would create all the connections between the function blocks. And then you would, okay, that was an event connection. Here's a data connection. And then finally, you would parameterize them. Okay, and again, I think most of you are familiar with this. The basic ideas are in part 1 of the standard. The XML coded configuration commands are, actually, I think they're in a compliance profile, although I may be wrong. Okay, let's talk about an open distributed system architecture. What does open mean in the context of open distributed control? It has 3 key attributes, and these are defined in part 2 of the standard, which is part 4, which says these are the things you have to define how you're going to do in a compliance profile. Portability, configurability. Okay, portability basically means software tools that can exchange library elements, software components that can actually exchange full system configurations, in theory, from multiple suppliers. Configurability means, again, that software tools can configure devices and software components from multiple vendors in the distributed system. And interoperability, of course, means devices can work together, even though they might be from different vendors. Okay, so the 1499 solution for the open distributed architecture is portability is done through the software requirements in part 2 and the XML encoding of software, the elements in software libraries. Configurability is done by standardizing the management protocols, which are given in parts 1 and 4. And the interoperability basically comes from a standard data transfer protocol. It doesn't standardize anything at the transport layer and below. It only standardizes the payload, and this is not required. You can use other encodings, but then you just simply have to use different parameters to your communication function blocks. It uses a standard way of specifying this, which is ASN.1, which gives you a very compact representation for data, which used to be important when field buses weren't fast. Okay, so what's the advantages of the 1499 architecture? It has simple event-driven execution control, which is suitable for fine-grained distribution and redistribution. It's really domain independent. You could even use it in information technology type applications, as well as the operational technology, OT applications. You can use it in edge devices, which are trying to converge the two domains of IT and OT. You can use it for IoT. It's really independent of the domain. It's programming language agnostic, which we discussed. It's communication protocol agnostic because you can configure the service interfaces with parameters that specify what the underlying protocol is. It's agnostic to the I/O architecture. You can have standardized I/O blocks, which you configure with parameters. And there are no global variables, data and variable changes. Anyway, all of that synchronization is performed via events. You don't depend on one thing executing, then another thing executing in some implicit order, because the events give you an explicit order of execution. So, what's been happening since 2005 when the first 1499 standard came out? What are the things that have happened that have made industry, the fourth industrial revolution, or that have enabled the fourth industrial revolution beyond what the holonic manufacturing systems were able to visualize? Basically, what's happened is this structure of cloud and edge computing, which involves massive data centers, which can support big data and AI. They support containerization and orchestration of applications, which gives you on-demand, always-on computing, very high-powered computing. It has various ways of delivering this in service-oriented architecture, software as a service, platform as a service, and obviously it supports distributed computation in ways that really could hardly be visualized back in 2005. The other thing that's happened, it's clear that the internet has become ubiquitous and the underlying transport protocol is going to be TCP in almost all cases. Another thing that's certainly become very important since 2005 is the concerns for cybersecurity. And the other thing that's happened just because of Moore's law and a lot of inventive software engineers, there has been growing functionality and complexity of the embedded software. So given that, what's next for 1499? The stability date for that standard is this year, which means we have to prepare, our working group has to prepare a maintenance report with a proposal for what should go in the third edition. And there's a fairly limited number of items under consideration, as opposed to the 278 or whatever it is, little items. What we have instead is, let's see, 8 plus 5 plus 6, 19 big items. Most of them are big. Some of them are just, a few of them are just error corrections or clarifications. But some of the important ones, which will make 1499 more suitable for the new computing and control environment that we find ourselves in, is streamlining execution control charts for simple function block types, and we'll see that. I'll give you an example of that. One that is pretty clear is the client-server service interfaces that are defined in 1499 are for one client per server. Well, obviously, today's system architectures, especially in IT, servers can serve many, many different clients. So there's a proposal for how to handle multi-client servers in 1499. There are also some proposed XML schemas for 1499 Part 2, which is a more modern way of dealing with XML. Those items are finished. In review, there are 5 items. I just wanted to go over a little bit some of the library management, which becomes a larger issue as you're trying to work in larger environments with multiple vendors. And there are 6 items in work. So let me just give you an example of a couple of the items that are in work then. Is a revised definition of simple function block types. In the existing 1499 standard, simple function block types are just a way of dealing with IEC 61499 event-driven versions of the functions and function blocks that are in IEC 1131. But what we saw was a large demand from users for simple function blocks where one event triggers one algorithm, which then triggers one output event. So for example, on occurrence of an event at input EI1 here, ELG1 gets performed and EO1 gets triggered, and then you're done. And so there's no underlying state machine with transitions and with transitions between the states. It just gets triggered and it happens. So that's these are some definitions then that are introduced. So this is a simple EC state. A simple ECC is an ECC that consists only of simple EC states, and then the simple function block type is a function block type whose execution is controlled by a simple ECC. So here's just an example of that. So here's a function block for computing the average of a number of real inputs. So in this case, it has basically 2 simple states. There's an initialization and a request, and the request, of course, does work. So here's the reset, which just sets all the variables to their initial values, and this is written in ST, and then the update algorithm is written in Java. This is just an example of how you can use multiple languages. And you can see that this simple ECC is much less complex than what the ECC would find in a basic function block. It has to have an extra start state. It has to have 1, 2, 3, 4 transitions. So instead of having just 2 entities in the ECC, you have 5. And when you see how it compiles into C++ or into Java, you see that there's a lot more that's involved because you have to track what is the active state. You have to make decisions when an event comes in, where to go. So it's just very simpler. It can be much more efficient. And actually, it's a much better fit to a microservices type of architecture where you want to get in and out quickly, such as Amazon Web Services Lambda is an example of the kind of service you'd be using this for. Okay, and the second example that I want to give you is library management. So there hasn't been a library management model in either 1499 or 1131.3. The only thing you have that's kind of close to it is the PLC Open Exchange format, which has a way of dividing things up into projects. I'm not sure that it deals with libraries or not. The idea being that here's your program development system, and it works with source packages, which may come from multiple suppliers. And so you need a way to identify these packages as to where they came from and what's in them. But you also have runtime libraries. So typically supplier A will supply the runtime libraries that go with the source library, and similar for supplier B. So the engineering support system puts these all together and builds them into a runtime library. So that's the model. It's relatively simple. You can, if you're familiar with Java naming of packages, you'll see. So these are all packages. Okay, if you're familiar with the Java naming of packages, you'll see that this is what's proposed here as well. The real problem has been with 1131.3, it uses the term namespace, and it uses it in the standard more than 100 times, but it has no formal definition for it. But, there's a section of the standard that carries definitions. There's no definition. And there is an informal definition given in one place in the 1131 standard, which it has no teeth, believe me. So what we tried to do here is we give set theoretic syntax and semantics for these terms. Namespace, library element name, fully qualified name, package name. These are all, or several of these, such as fully qualified name, basically come from Java. So these are the names of things. And then how these named things are put together in other named things are defined in terms of library, element, package, software library, source library, runtime library. And the way they're implemented in the 1499 declaration language is package and import. And they're pretty much like the Java ones. But again, formal rules are given for how those things have to be put together. And that one is pretty well complete. There are open issues that really have to be addressed in compliance profiles because there's no place in the 1499 standard for dealing with it, at least for the time being. And these are how do we deal with cybersecurity? Is there anything special that 1499 has to do? Or do different compliance profiles use different security provisions? The answer is still unknown. The other thing that needs to be done, and again in a compliance profile, is you need what's called an IEC 1131 compliance statement for those parts of the 1131 standard we're going to use. So it has to be there for data types, for the structured text syntax, for the ladder diagram and function block diagram features, and for the standard functions and function blocks that will be supported within the scope of the compliance profile. So these are all things that still need to be done. And this is just a little reference page where to find information about 1499 tools and runtimes. I think you're all pretty familiar with these. The next control is now part of Schneider Electric's programming tool set. Isograph, that's a long story, but it's basically a licensed technology from Rockwell Automation. It's for essentially for people who want to use that technology in their own devices. Okay, and here's just some places to get more information about the JADE, Java Agent Development Environment, and then the various program development and runtime tool sets. Here are just a few handles on ResearchGate to follow. Check our papers, including the referenced works. Check the co-authors and the projects of these folks, because it's sort of like a branching tree. If you start here, it's not even a tree. It's a network of interrelated research. And you can find a copy of this presentation under my handle. It's PDF, so it doesn't have the nice animations. I think I'll probably upload the file of the. I developed it in Google Sheets, as you can see when I was projecting it. But I think I can probably put out something like a PowerPoint file that has most of the information in it. Okay. Oops, and in this presentation, here's where to find the PDF. Okay. And I'm done. Thank you. And one final wish. Happy midsummer.
Thank you, Dr. Christensen, for your great talk. So, dear colleagues, it's time for question. So, you may raise up your hands. It's near menu. So, Dr. Christensen, I have a question about connectivity in the standard. If you speak about distributed system, we assume parallelism, physical parallelism of the computers. And parallelisms mean, for me, some unpredictability in message passing. So one message, if you send several messages in parallel, there is some unpredictability which message will arrive first, which method will arrive second, and so on. So questions is what we can find in the standard. They deal with maybe standard data transfer protocols, or maybe so-called virtual bus, IEC 61499 virtual bus. What do you can comment this question about unpredictability, or maybe formal semantics of the communication in systems based on the IEC 61499 standard? Are some problems, or maybe it's quite okay?
Yeah, I understand the problem. I don't know the solution. One thing that can be done, of course, is I'm trying. Does TCP? No, even TCP does not guarantee that messages that are not in the same packet won't necessarily arrive in the same order as they were transmitted. Yeah. Especially in a distributed system where messages are switched through gateways and routers. If the system can't guarantee it, then higher level protocols have to guarantee it. And what I would say is, if ordered, if it's a necessary constraint that each message be received, and that the messages be received in the same order as they were transmitted, then you obviously have to have a mechanism for numbering each message, for buffering the messages, which is the same thing that TCP does for packets, for messages when they're individual messages when they're broken into packets. But yeah, this is an issue. Again, I think this is an issue for the underlying data transfer protocol. I'm not sure it's an issue that can be solved by 1499. If you had such an underlying protocol, of course, you could just specify it in the parameters of the blocks. Use this wonderful messaging protocol. But aside from that, I don't have an answer within the context of 1499. What I say is that you need some sort of reliable messaging protocol underlying it.
Okay, thank you. It's issue and challenge that
the
must be solved within the standard. I see. I see a question from Valery Vyatkin, from Dr. Vyatkin. Please, Valery.
Yeah. Hello, Jim.
Hey.
Okay. I think my camera is not working anyway. We're not losing much with that without the camera.
Oh, there he is.
My question is the kind of question which I often used to hear from various audiences. Basically, the question is, how do you explain that the standard has not experienced mass adoption by industry yet? After how many years of development, and after being formally finalized in 2005, 16 years back, it's still not very common technology in the industry. So do you have any rational explanation for that? Why it has not been adopted like immediately?
Well, for one thing, I don't think that the demand for agility developed in the way that it was anticipated by the Agile Manufacturing Report back in 1992. Because and why did it not go that way? Because the agility in the manufacturing plant wasn't as important. I think the reason is that the customer demand for product variation, much of it was realized in software, in the product. And I think that was not anticipated. Okay, smart products, right? So I think that a lot of the variability and customizability actually occurred basically through the distributed app architecture instead of through the distributed control architecture. And the other reason is installed base. It wasn't really possible to build a fine-grained architecture on top of PLC architecture, which everybody was used to. And so the advantages of adopting the new architecture were not greater than the cost of converting to the new architecture. And I think that's the problem. Because you had an entire base of technicians who were trained in the PLC architecture. And that whole base would have had to have been retrained. And so I think the real problem was that a clear migration path was not established. And so two things. One, there wasn't the demand for the highly flexible, reconfigurable manufacturing systems that was anticipated. And the other was the installed base issue. And I think what we're seeing now is if Industry 4 goes ahead, what you're going to see is instead of the flexibility being built in at the factory floor, the flexibility is going to be built into the supply chain. And you'll begin seeing things like, well, in fact, you're already seeing it, supply chain marketplaces. So that the people who need products built can negotiate the pieces of the supply chain and coordinate the pieces of the supply chain, just like those agents would have done on the factory floor. Is there a place for 1499 in that kind of system? I would say yeah, because the place where you're going to see all the agility and reconfiguration is going to be at the edge. At the edge and higher. This is just my guess. Will it become the technology of choice for embedded control? Just don't know. But it does have some advantages. I mean, in terms of encapsulation and reuse, if that becomes a big issue, which I don't know if it will because of this, because of the global supply chains, you're just not going to need the reconfigurability. It's the suppliers, the people that are manufacturing and selling into the global supply chains. Those are the ones that are going to need the flexibility and the reconfigurability. But again, like for instance, if you're in the business of producing printed circuit boards, all of that flexibility is already in the software of the printed circuit manufacturing. Maybe, but anyway. But yes, it's the folks that are at the front end of the global supply chains that will need it. If that evolves, that's where it will evolve.
And also, quite surprisingly, the most enthusiastic kind of current hype of interest to 61499 comes from sectors which are quite far away from like the classic sort of model industry 4.0, namely from oil and gas industry, right? So as we know, that is a like very broad adoption and experimentation in large oil and gas industry with IEC 61499 rather than in manufacturing.
Well, the reason for that is that the traditional DCSs have very little flexibility to change their control algorithms on the fly, which is something that the more advanced oil and gas processing companies have very advanced control algorithms that they develop themselves. And it's really quite difficult for them to switch them in and get them deployed to their factories. So what they really need is they need a new and more flexible distributed DCS architecture. And the reason they need that is because they can actually do that in software, because they have this large fixed plant, right? But it has a lot of control on it that can be reconfigured in software. Right now, it's just too much of a job for them. It's very difficult. Like I said, it's very difficult for them to deploy their advanced control algorithms into existing plants. And of course, the big upset was when Honeywell made their entire distributed control system line obsolete and said, yeah, you're going to have to convert everything over to this new system. Oh, and by the way, your old software won't run on the new system, and we don't have any tools to help you make the conversion.
Yes, dear colleagues, we slightly go to the panel discussion. So we have one question from the chat. Adianta Dvi Admojo. I am sorry for pronunciation. The question is, if you are asking to guess how the IEC 61499 standardization will address cybersecurity. Several questions. And what would you think that cybersecurity will apply separation of concerns, that the standard abstract away communication protocols from the application logic? So you may read the questions for memory.
Yeah, I think that, from the 1499 point of view, there are, I think, two problems that need to be addressed. One, of course, is the security and reliability of communication between the devices when they're operating in real time. But even more significant is, how do you provide security of access? And since it has this feature of reconfigurability, you want zero break-ins into that configuration process or capability. And so what you need is what's it called? You need the kind of security that verifies the identity of whoever is trying to make those configuration changes. What's that called? Authentication. You need authentication protocols, and it's especially, well, you need it in both places. So again, yes, I think that you can have an underlying communication service that provides the appropriate authentication protocols. And that's all pretty, but how you manage that is another issue too. How do you manage secure messaging and authentication? There's just a lot of underlying platform services, I think, that have to be provided to do that. Again, so let's say it again, secure communication and authentication. If you solve those issues, yes, if you solve them at the communication protocol issue, then 1499 will be fine. But how you do it and how you call out how you call out and manage those services from the 1499 level, I think could be an issue. But then again, you get into the issue of how do you manage device services in general, the devices or the services that are provided there. Interfacing to them is easy. Managing them is might be separate issue from 1499. I'm not sure because I'm not an expert in the field. I know the issue is there, clearly. So, but the real question is which functionality should be partitioned into the 1499 level, which is really an application level, and which should be just provided by the underlying resource. And how do you interface to that? I think the answer is the way you interface to that is by appropriately parameterizing your communication parameters. Yes, because of the separation of concerns, that concern can all be offloaded in one place, which is the communication service. As long as your communication service is secure and well authenticated, then you can also do configuration with it as well as your real-time messaging.
Yes, thank you. And also, we among the participants, we have some people from the number one IEC 1131 part 3 company. It's Codesys company. I see Manfred Werner and Martin Decker. Maybe they can enlighten the questions why the industry still does not adopt the standard, and maybe some opinion. We are ready to listen this opinion. So, dear Mr. Werner, or maybe
yes.
Mr. Decker, yeah, yes.
My name is Bernhard Werner. I'm the brother of Manfred Werner, and I was asked to replace him today.
Yes. Nice to see you.
The reason is that I actually worked on the standard. Maybe Jim Christensen remembers me. We met in 2008, I think, in Cleveland. When you were the last time with us and working on the 3rd edition. So, and currently I'm working on I'm part of the working group on the 4th edition. And yes, we do a lot of bug fixing, including the namespaces that you mentioned. And this is my job. So the question was, why not 1499? I think Jim Christensen already gave the answer. There is not an installed base. And the demand is not as expected for things like that. People like their centralized system. They have one big system that does everything, and it gets bigger and bigger and bigger. The programs that we have today couldn't be imagined in 2000. I think it is just it is not different from PC programs. The software that's nowadays in a PLC is very complex and very large. And then maybe our customers are also mainly in the factory automation. So maybe Valerie Yatkin is correct to say that oil and gas industry is a little bit different. That may be correct, but we don't know that. And but there may be also some problems with the standard itself. I can only say what I like about 1131 and especially the object-oriented extensions there. It gives you a great flexibility on how to build your system. If I see the blocks of in the 1499 with a server and a client, I would like the message that is passed between those to be an object. This is something that I can easily build with the 1131 object-oriented extensions. I can pass an interface, which is a handle to an object from one function block to the other. And I always see problems with this kind of architecture in the 1499. I don't know whether that's possible. So I think the 1499 has a clear model for modeling your applications, but it is also maybe a restriction. That may be some inherent problem of the 1499. Something that I see, but I'm not a 1499 expert. I read the book from Mr. Vyatkin and only the first part of the standard.
Yeah.
Thank you for your opinion. Maybe some comments.
That might be an interesting addition to 1499, since 1499 does depend heavily on 1131 data types and the programming languages. So if you can consider an object as being a kind of data type which just happens to have methods attached to it, right?
Mm-hmm.
It may be possible to think about that. To some extent, the adapter interface does that. To some extent, structured variables do that. But yeah, okay. But there's no mechanism for dealing with it directly, that's for sure, to pass objects. But well, let's see how that works out and how well. I guess it hasn't been well accepted, the idea of passing objects as handles. Has that been well received? Is there a demand for that?
Yes, if you think about motion control function blocks, like in the PLC Open, then there you have the motion, which is the move is the function block. The move is the object, and the axis is passed as a handle from one to the other. In our system, the axis is an interface to an abstract object. And this is covered by the PLC Open motion control function blocks. So this is, I think, sometimes quite a
So that would be a good place to look to see an application of this passing objects, to see if there's a way to maybe do.
In my opinion, maybe I'm not correct, but in my opinion, the 1499 way to do this would be the axis is the function block, and the move is an event that I send to the axis. The move absolute, for example. Am I correct in this?
Yeah, probably. I haven't looked closely enough at the PLC Open motion control function blocks to really have an opinion on it. Because what you're looking for obviously a very convenient way to pass something, a command with its parameters.
Yes, and an object that has its own state, internal state, and the move absolute, for example, has its own internal state, because you can start it, you can stop it, you can interrupt it, or you can ask it, is the move still active? There can be more than one move active at one time. So
actually, maybe a way to handle that would be using REST, representational state transfer, where you send you have a data structure which you give all the information about your current state along with the message, So I think it might be, you're right, I think it might be an event with associated data, which would include the state. But I don't know. I don't, I just don't, I'm not familiar enough. But I think REST is really a very interesting concept because it lends itself very well to the simple function block idea. You can actually have state, but you just send it as part of the message, which is, it's good for distributed systems. It's a good way to synchronize states without having to request the state. Every time you send the command, you send your state with it. But anyway, it's just that's just off the top of my head.
Yeah. But I just think that some things are more easily done in 1131 because it does not give an idea of the architecture. It is not so structured like 1499, which gives a clearly way on how to do things. At least that is what might be what you can think if you see the example applications. Here's my sensor, here's my actor, here's the link between it.
Mr. Werner, may I ask the questions? Do you have some statistic for the IEC 61131.3 standard? What kind of language now is most popular? I know that several time ago in 2006 year there was statistic, you published statistic with Roland Wagner that about the most popular language of the IEC 61131.3. Do you have the same statistic for?
I don't have the numbers right now. I think we once made a survey, but it is not representational. It was only in what's it called, LinkedIn. And then many people voted for a sequential function chart, which was a little bit surprising. It isn't even really a language.
Yes.
But it is not representational. I don't have the answer. What I can say in our tool, very obviously, strap to text is the most popular language.
Yes.
It is also most suitable for the object-oriented extensions. And then.
So the situation is really the same. What about statistic about the tasks the user try to solve? Maybe just motion control mostly, or maybe just discrete control, maybe logic control.
I don't have.
Do you have some statistic?
No, I don't have. It's very sad. We would really like to have this. We have, but I personally don't have, and I think not the company doesn't have it either. But I'm also. Oh, I just got a message from Manfred. 10% do motion control. Okay, this is with our tool. 10% do use our tool for motion control.
So it's maybe some just problem that someone deal with only motion control, and that it's all that he wants somebody do with complex control algorithm, for example, single crystals, growth, furnace, Chokralski methods, and that is different kind of algorithm, different kind of strategy, different kind of maybe.
Possibly, yes.
That means, as understood me, that your point is understandable, that centralized system is simple. So centralized simple, and simplicity is that we already want simplicity, but the life is maybe sometimes give us more complex case study. For example, if you open modern car, we see inside maybe 100 microcontrollers in modern car that provide control algorithms of the car. So it's just example of distributed system, and we ought to look at the fact. And really distributed control means parallelism, and from psychology point of view, human being doesn't like parallelism. It's very complex things for him. But the life says, and for example, if you see it, for example, Internet of Things, it's very simple system, because I personally have no idea which way, for example, the iron can communicate with air conditioner, or maybe with lamp, or with cooler. I have no idea. But in industrial Internet of Things, the situation is different, because modern plant is very complex system, and every subsystem communicates with each other. They implement some one purpose, some one goals to. This is the problems. It's a matter of facts, and I see yes, we know that the codices is number one. That you buy next year, you buy Siemens, yes, for number of installating software.
Do you have numbers?
2% more than Siemens. Codices by Siemens, but the thing
I'm not sure about that, but we are quite successful, yes. So
yes, the great company Codices, but the things that maybe it's good things to look forward for. For example, to invest in to research the things, some case study to solve this complex question, because in my opinion, IEC 64099 is very attractive things in their base. It's mostly distributed ability. You can make centralized algorithms and then distribute it on the several or many computers. It's very good idea. It's excellent idea. So that's my opinion. And another good thing that the standards allow us to use event-driven strategy for automation. So we can process events and generate reaction. It's in my opinion, it's allow us to use so-called application-centric paradigm for control algorithms. Application-centric, and comparing to device-centric or instrumental-centric, as it used in IEC 61131/3. We in the first standard we start from a computer, but in the 4099 standard we can start from algorithms. We can, and what I personally see that a lot of algorithms that created within 1131/3 standard, it's impossible for reverse engineering. It's very hard to maintenance. It's very hard to understand what kind of thoughts we will be was used by the programmers. It's problem of the standard, and we need the next step. And I see that Dr. Christensen's Christensen show us the right direction for the achievement. Thank you.
Oh, just thinking about the Internet of Things, you want it to work like this. Alexa, turn off table lamp.
Yes, yes. Can you show us which way your, for example, iron or maybe communicate with, for example, from fragile, from your from maybe for your light, for lamp? Is it possible? It's absolutely, from my point of view, absolutely separate things comparing to industrial automation.
You see what's happened here, of course. It really is that command goes all the way up to a server, gets decoded, and then comes back down and goes out to the table lamp.
Yes. If there is some connection, it's very simple, in my opinion, comparing to the industrial automation. There is pump, valves, and so on.
Yeah. It's this this whole vague idea of the Internet of Things out in the cloud. It's like that. It's not like controllers having to communicate with each other in real time and being able to configure that communication and reconfigure it quickly. Anyway, so yeah, but yeah, because what you're seeing is just this example of the technology evolution that I was talking about, that you can get in and out of the cloud on a human time scale very quickly, and that's what it does. Which means, for instance, that you can operate a chemical plant just as well, if not better, than a human operator. As long as you can maintain that connection, because on the other end, the services are packaged up and coordinated and very, so the other end is pretty reliable. Although I guess AWS had one server farm go out and shut down the whole East Coast for a couple of hours. So that would not really be acceptable in a chemical plant. Yeah.
Thank you. Dear colleagues, maybe some... Professor Vyatkin, please.
I just wanted to add a little bit to this discussion on kind of cloud-based automation. I encountered some kind of, not a fight, but a bit of argument between proponents of let's say totally IoT based approach to future automation, which is based on a multitude of communicating smart devices. And this is that's probably the vision that has been from the beginning of this IEC 61499 development, and quite orthogonal model that comes from telecom industries, right? And these telecom guys are quite powerful, and basically they have enough resources to overturn in a night all the industrial automation business. Like imagine Huawei tomorrow decides to enter automation business and swipe off all the vendors and substitute them with a big cloud, and whatever approach to programming and development they may want to propose. And it's been like in several discussions, this kind of cultural gap shows itself that so the telecom people, they experienced quite a big success story when they completely moved to computers from the telephone exchanges, which were kind of electromechanical devices, towards total computing, and they are very inspired by this success. And they see like this model can be, applied everywhere in the world. And with a link kind of latency getting better and better, they start pushing this model towards physical world like industrial automation.
Yes. By the way, this morning, some research group from Huawei make a talk. Unfortunately, it was night in USA. Maybe it's too late in Novosibirsk. But there is a problem, and they really talk about their problem in automation of telecommunication system. And I have a feeling that the approach, the following, they use device-centric paradigm to construct elementary devices, and then so when they build complex system, they use configuration approach. So they make some device that can be configurable when they build telecommunication system, big telecommunication system. So this two kind of approach on the low level and the high level. Yes, it's very interesting idea to look at the telecommunication system. Maybe there is some new idea for us.
But the good news is what Bernard has said about the scale of software. So software automation software becomes huge. And it wouldn't be possible to migrate it overnight to any sort of new platform. Just because it's quite huge, and behind that there's a lot of effort.
Yeah, but this shall be a secret. People get dependent from the software. Yeah.
Or, dear colleagues, some other opinion? So, dear colleagues, I want to say that our discussion is very fruitful, at least for me. I am very happy to see here Dr. Christensen and Dr. Vyatkin, and insider from the #1 Codesys company that express their opinion and make some new idea for future development in this direction. Thank you. Maybe Dr. Christensen, couple of words.
Oh, a couple of words. Well, it's been a great pleasure for me to get together with people that are working in the same area and to have these technical discussions, because it's been a long pandemic, and I'm glad we're finally coming out of it. But I am glad too that we've had this opportunity to get together, with quite a variety of folks. And also it sort of forced me to think about some of these issues again, because I've been busy with some other stuff, which some other organizational stuff. All right, I'll tell you. A church reorganization. It's been very hectic, but that's pretty good. That's quieting down now. So I think this gives me a good opportunity to get back into some of the technical areas again. So I very much appreciate this invitation. I appreciate everybody coming by and participating in the discussions. So thank you all very much.
Thank you a lot. Mr. Venner, couple of words?
Couple of words. I was also glad to be here and to see Jim Christensen once again after many years. And thank you for the invitation.
Yes. We see for maybe some common investigation, some project. Okay, thank you. Thank you. We are looking for you, for the company, for this big company. Dr. Vyatkin, please.
Yeah, thank you very much, Vladimir, for organizing this session and inviting me. And I was happy to share the link with some of my colleagues and students to join this session. I hope it's fine with you. So that was a unique opportunity to catch up again with Jim, with his colleagues from CodeSys. So fantastic, and automation is a cool stuff. So we are doing really great, interesting, enjoyable research and development.
So, dear colleagues, thank you you a lot. Thank you very much. See you next time. See you. Okay.
Next time.
Thank you. Bye-bye.
Bye.
Bye-bye. Dear
Thank you.
organizer, our dear hosts, Zamba, yes?
Yes.
Yes. We can switch off the records. Okay. And
recording stopped.
Yes, is it possible to get records to share it between the participants?
Yes.
Yes.
So should I send you to you by email or something like that?
Yes, by email, please. My email is I think you know our emails of the organizer, but for the case. Wait, maybe this one. This private mode. Okay. You switch your microphone off.
So I think to my
ZYUBIN at IAE.nsk.su. Okay?
Okay.
Can you share the link?
Okay, I just show your email using.
Yes. You can copy it to.
Yeah.
Or maybe you can see it at the our workshop page. Yeah, so maybe can you send me your email,
Okay.
your contact?
Yeah, I will send you my notification.
Do it, please. See no message from you. Yeah, okay. Thank you a lot. Thank you a lot for great technical support for our workshop. Thank you.
Vladimir,
Yes.
can I just ask you a couple of questions? I know that it's quite late in Novosibirsk.
Yes. Wait.
quite yeah.
About 11
What
evening.
yeah, I'm just wanted to ask, what about like your area where I'm working now, and what is your
We are working.
research interest in?
We are working in process-oriented programming, such a kind of
Because I
programming.
heard a lot of like information about technical information, technical details about like in manufacture details. I'm wondering from what resource do you get this? Because-
Yes, Nikolai, I can share my email with you.
Yeah, maybe.
Okay.
I'm also familiar with
To make a conversation more
Yeah.
comfortable conversation
I will be very glad.
by email to yes. Uh-huh. Yes, I sent my
Yeah.
email
I get it.
as a private message. Yes.
Yeah. Thank you very much.
Okay.
We will,
Please send me a short email and we can conversate.
yeah.
Or maybe we can use, for example, Google Meet.
Sure.
Okay, so.
I can send you my like university
Yeah.
email, or like it is like LTU, because I'm working on LTU. I'm working with Valerie, so
Yeah.
it will be fine.
It will be okay.
Okay.
So, by the way, one of our postdoc, we plan will arrive to the Dr. Vyatkin's lab. Maybe
Yeah,
this year, maybe next.
I will be in this year. I will be in this lab. I will be
Yeah,
invited.
I see. Yeah. I don't understand.
Have you received this,
So yes.
Nikolai Alkin?
Yes.
Thank you very much.
Thank you.
For your information. Thank you for all. Bye.
Bye. Mr. Zamba, thank you a lot.
Thank you, everybody. So I'm going to share with you my drive. I will put the record in my drive and write out it will be accessible from over there. I think that
Yes.
it will be more easy.
Some problem with sound. I will send you email and ask you for the link. Is it okay?